Thank you all for being here. Happy Tuesday. I wanted to do a couple things, but I wanted to make sure that you were ready to go once we get to that point. On today's announcement, below where you just clicked to get here, there are a couple things that I want to make sure you have open and ready for when the time comes. We've got a couple things that I think will be pretty helpful for you. The first link is to today's practice that we'll get to in a few minutes. So have that one open, ready to go. There'll be the part one is all the stuff that we'll do together. I want to make sure that I really go slow and work through each one with you because there's some different things that happen that I want to make sure you're ready for. Below that is a link to a completed unit circle in case you wanted to have a fresh one up. You can also just take out yours from yesterday if you have it and you like it and it's legible and it's nice and it's correct and it's all good. But if you want to make sure that you're picking out the right angle measures or coordinates or whatever it was, having a completed unit circle out ready to go, also really, really helpful. You're going to see that everything that we do today is me going back to that unit circle, okay? Below that, I put a link to a blank one in case you wanted to practice. Like I said, I might have said yesterday, if we were in class, we would keep practicing, like kind of filling out a blank one so that you would get more and more familiar with it. And I try to figure out some of the really nice ways to remember how to do it without necessarily having to rebuild it every time. And I know I talked about that a lot yesterday. Like you can build the unit circle yourself with knowing the degrees, being able to switch to radians or vice versa, and then using special right triangles. That is all good, right? That's all really helpful. So, but that takes practice. But that's on you. That's totally up to you. We're not gonna have like a blank unit circle quiz or anything like that. It's not really something that I think you really need to have memorized to get to that point. So no worries, Riley. All good. Good to see you. But what I wanted to do was give you one of those tricks. There's a really, really nice trick for the hardest part. I'm just going to scoot us a little closer here. The hardest part of the unit circle, in my opinion, are the coordinates and knowing what to put where. And so what I have here, it's a little glary. I wonder if... Sorry, I just wanted to get you nice and close so you can see what I'm talking about. If I can get you, let me go the other way. Little angle, but good enough. Okay. Let me turn. Those lights need to stay on. Okay. What I did was I drew the first quadrant right here for the unit circle, and hopefully you can see that. Okay. I know it's a little glary, but you have it in front of you. I just wanted to show you the trick that goes with figuring out which coordinates go where and in what order. Okay. Because if you know the first quadrant, you can do all of them because they're all the same numbers, just switch the signs, right? 30 degrees up from here, or 30 degrees up from there, or 30 degrees down from there, all the same numbers in the same order. They're all just reflections, which is really nice. Okay, here's the trick, and this is amazing. And I actually only learned about this like last year. So I can't take credit for it, but it is really, really, really nice. Okay, so remember a couple things. Number one, if you are on an axis, so 0 degrees, 90 degrees, 0 radians, pi over 2, the numbers are just 0 or 1 or negative 1, right? So you don't have to worry about these fractions, okay? But if you are inside a quadrant, these are the three numbers that you want to make sure you know are going to be there. 1/2, radical 2 over 2, or radical 3 over 2, right? All of these fractions all over 2. So you don't have to really worry about that. No matter what, I know my denominator is just going to be a 2. Really, the only thing I have to care about is what the numerator is going to be. And yeah, technically, like there's a square root over all of them, but the square root of 1 is just 1. So we don't include that square root there. But square root of 1, square root of 2, square root of 3, all go on top, okay? Here's how you can do it. It's called the left hand trick. If you have your unit circle in front of you, like take your left hand, okay, and your 5 fingers on your left hand are going to represent the locations of the angles in the first quadrant. okay? Where your thumb is the x-axis, okay? And your pinky is the y-axis, okay? Those I don't really have to worry about, right? It's really just the 3 inside here, okay? My index finger, my ring finger, and my middle finger, my ring finger, okay? Watch this, this is so cool, okay? If you were to look at, let's say 30 degrees, pi over 6, okay? That's my index finger. Look what happens if I drop my index finger. Like I kind of tuck it back, right? So that one doesn't exist anymore. And I've got these 3 and then this one, okay? Look at what we have. You have 3 and then 1, right? As you look from left to right, right? Because there's my hand, right? From left to right. Look what the order is, 3 and 1. And look at the order of the x and the y's. Radical 3 and then 1. So by dropping down 30 degrees, the finger that represents that pi over 6 spot, it gives us not only which coordinates, but in the right order. It tells us that the radical 3 part's going to go first, and then the 1's going to go second. Of course, they're all over 2 to get you there, okay? Drop down your middle finger and do the same thing, right? Because that's 45 degrees, and look how your hand gets separated, right? You've got 2 fingers here, a space, and then 2 fingers here, and look at the coordinates at 45 degrees. Radical 2 over 2 and radical 2 over 2. Okay, and so the number of fingers that are up separated by that spot tell you which number is going which spot. It works, of course, for your ring finger as well. Drop your ring finger down for 60 degrees for pi over 3, 1 and then 3, 1/2, and radical 3. So cool, so cool. Okay, so I just learned that like last year, and I use it all the time. Seriously, if I'm sitting there and I'm just trying to figure it out, like I sit there with my fingers like this, right? 30 degrees, 45 degrees, 60 degrees, and it gives me the order of the coordinates, which is so cool. Okay, so it's called the left hand trick. Feel free to steal it, write it down, look it up if you want a refresher on that later on. If you just Google like left hand trick for unit circle, it'll tell you what it is. So really awesome. I hope that's super helpful. Okay, cool. So picking up kind of where we left off yesterday. Okay, with these last few things that we did that we kind of snuck in right at the end, hopefully you had a chance to get those down. We have our 3 basic trig ratios, right? Cosine, sine, and tangent. And trig proportions, yeah, that proportion word is just a little too long, so I'm just gonna start using the word ratio. It's gonna come up probably a little bit more often, but proportions, ratios, same thing. But we've got, it looks like a negative, it's just there we go. All right, x over r, y over r, and y over x. And then their reciprocals right across from them, right? And I know I talked about them being co-functions, but it's really like the most important relationship you want to understand is that every basic trig ratio, the ones that come from like SOHCAHTOA, right? Sine, cosine, and tangent, I put them in this order on purpose. You'll see why here in a second. If you're period 4, you watched period 4 yesterday, you didn't get this last part, I'm gonna give that to you right now. I put their reciprocals right across from each other, right? So cosine and secant are just reciprocals of one another, x over r, okay, flip it, r over x, right? Same thing for sine and cosecant, same thing for tangent and cotangent. So you have your 3 basic trig ratios and you have your 3 reciprocal trig ratios. And I think I called them co-functions last time. If I didn't, it's all good, kid, you're good. I wanna make sure you understand why I'm calling them co-functions and how that might be useful for you once you get to what we're gonna talk about today, okay? Every trig ratio either has a co at the beginning or it doesn't, right? Cosine does, secant doesn't. Sine does, sine doesn't, cosecant does. Tangent doesn't, cotangent does. And what I want you to realize is that when you're trying to figure out what reciprocal function, what reciprocal ratio we're looking at and which one it relates back to, that these pairs a function and its co-function. One of them has a co and the other one doesn't, right? So if you know that sine, cosine, and tangent are your three basic trig ratios, and you're trying to figure out, okay, which one of these three am I relating myself back to? Because they're not going to tell you, right? They're going to say, hey, what's secant of pi over 2? And you're going to want to know, and you'll see why here in a second, which one of our basic ones we want to go back to. Clearly, cotangent is the co-function for tangent. That one's really easy because the word tangent's right in there. But with secant and cosecant, none of the word sine and cosine is in there. And so what I want you to know, cosine already has a co in it, so its reciprocal doesn't. And so when I'm thinking about secant, I think about the word secant, and I look for a co, a prefix of co. This one doesn't have it, so I know its reciprocal does. Okay, that's what gets me back to cosine. The word co-secant already has a co in the name, and so I know its reciprocal doesn't. Okay, and that's going to come in really handy for us right now when we start to think about what they're going to ask us to do when it comes to actually evaluating cosine and sine and tangent and all that stuff at the unit circle. Okay, and so what I really want you to understand, okay, and this is where I'm picking up with new stuff, okay, is that if we are on the unit circle somewhere, okay, I'm just going to pin me so I can see how big things are. Okay, so if you're on the unit circle somewhere and you're looking at the point, right, x, y, right, and I'm talking about like the point along the edge of the circle that we're tracking as we make our way around. If you are at the point x, y, whatever it is, and you've opened up an angle theta to get there, okay? So I stop wherever, right? And I open up an angle of theta. And I want to figure out what's happening at that spot, x, y, okay? Well, take a look at our first two trig ratios right here, okay? The basic ones that only have either x or y in them. And let's think about what happens when we open up whatever angle we're looking at, but we're in the unit circle. This is going to be a little bit more of you and me kind of talking. So I'd love for you to unmute your mic if you have an answer that you want to share. What's the radius, again, of the unit circle that we're looking at?
1.
Good. Okay, so cosine of theta is whatever the x value is at that spot over 1, right? And so dividing by 1 doesn't change anything. And so look at this relationship that we have. That the x value of any spot on the unit circle is exactly what the cosine of theta is going to be at that spot. So that if we type in our calculator cosine of 74 degrees, well, yeah, it's not a great unit circle spot because it's not a 45 multiple, but it is giving me exactly the x value of that coordinate that's moving along the circle. Well, 74 degrees isn't something really nice, but 30, and 45, and 60, and 135, and 7 pi over 6, and 11 pi over 6, and 7 pi over 4, and all of those really nice spots, we know every single one of those x values, which means we can evaluate cosine of any unit circle spot without actually having to do real trigonometry. We just have to know, or at least have in front of us, the unit circle, okay? And so what's really nice is that the point on the unit circle is going to be exactly the same for x as the cosine of theta at that spot, which is incredible because now we're going back to relating like this ratio of sides in a triangle to the location of a point along a circle, okay? Same thing happens when we deal with sine, right? R is 1. And so dividing by 1 doesn't change anything. And so the y value on that circle is exactly the sine of theta, okay? And we can use that fact to help us with tangent because then I can just do y over x at that spot and I don't have to worry about r. And all I would have to do then for secant is to take cosine and flip it upside down, right? To take x, the x value, and flip it. to do cosecant of some angle, I really just have to do sine of that angle and flip it. Okay, when I'm on the unit circle, because I know all those answers. Same thing for tangent. I'll just take, instead of y over x, I'll just take x over y. And because I'm on the unit circle, I know every single one of those spots. Okay, and that's what I want to do with you today, is I want to take some time to show you the kinds of questions that they start with in basic kind of trig evaluations. Let me slide this a little closer. So you can see how all of this is going to play out when we actually kind of start working through some problems. And so that's where two things are going to come in handy. One, having that unit circle out and open right in front of you, because we're just going to use that. That's all we need, and just a little bit of arithmetic. Okay. The other thing that I want to make sure that you have open is the link that I put on there for today's practice. Okay, I called it classwork 4.2. Nothing you have to hand in or anything. I just wanted to give you some time to try some things out. Okay, now these 12, I know 12 sounds like a lot. It's going to take us a few minutes to work through them for sure. They're all a little bit different, and I wanted to make sure that I spent the time going through each one of these with you to kind of at least even start us off kind of slow and then build up from there. But I'm telling you what, the only thing that I need is the unit circle and the understanding of these ratios that are here. But the most important thing is to understand that when we're talking about sine and cosine, that cosine is x and sine is y, okay? And the way that I remember that is that in the alphabet, x comes before y, and c for cosine comes before s for sine, okay? X, then y, so cosine and then sine alphabetically, okay? And so what I'm gonna do is I'm gonna work through with you these 12 problems one by one, so you can see how they all work out. I'll have a little extra practice for you after that, and that'll probably be it. We'll just kind of pause right there, and then we'll come back tomorrow and we'll kind of build on that idea. Okay, so remember this, x is cosine and y is sine. I'm gonna leave this up here for now so we can look back at it should we need it. And I'm gonna start way over here. Okay, just kind of working through each of these. Okay, so have that unit circle out, ready to go, and I would love to hear from you as we work through these, okay? All right, first one, sine of 30 degrees. Okay, good, you can see that. Okay, sine of 30 degrees. So go to your unit circle. Open up an angle to 30 degrees. And all I really care about at that spot when we deal with sine, cosine, tangent, all that stuff are the coordinates. And some proportion, some ratio that goes with that, okay? But when it's just sine or cosine, I only need either for cosine x, or in this case for sine, I just need the y value at that spot. So you tell me, open up the 30 degrees. What's the y value at 30 degrees?
1/2.
Perfect. Done. Sine of 30 degrees is 1/2. And if you have a calculator, the calculator is going to give you all that same information. You just got to be careful, because there are two modes that our calculator could be in. It could be in degrees or it could be in radians. And if you're typing in a degree measure, you better be in degrees. Because if you type in sine of 30 and your calculator's in radians, it's going to go to 30 radians. Okay, it's going to give you something weird. Okay, done. Sine of 1/2. Sine of 30 degrees is exactly 1/2 because it's just the y value at that spot. Okay. Cosine number 2 of 3 pi over 4. Okay. Now I know that there were no equal signs in here to start because we're not solving an equation. There's no missing variable there, right? They didn't set it equal to anything. And they could have. They could set it equal to x or y or whatever they want. But if it's just an expression, no equal sign, not an equation, then we're just evaluating and we just want to get a number back, okay? So same thing here, right? 3 pi over 4, no units though. So we know we're in radians and we want cosine. So we want to open up that angle to 3 pi over 4. And we want to figure out, because it's cosine, all we have to do is look for the x value at that spot. So do it. Open up an angle to 3 pi over 4. What's the x value at that location?
Negative radical 2 over 2.
Perfect. Okay, put the negative out front, not up necessarily with the square root of 2. Looks good. Done. Perfect. Okay. And the calculator would give you that answer as well. The problem with the calculator in these cases is it's going to spit out the decimal approximation for that. Okay. And so what I'm going to do down here, I'm just going to box off a little spot for numbers that are on the unit circle that are irrational. It's kind of nice to know what that decimal approximation is, so that if you are jumping into a calculator and typing in something like cosine of 3 pi over 4 and you're getting some decimal, it's going to be negative, of course, because that one's negative. But if you got the decimal 0.707, blah, 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 things going to keep going. Not in any nice pattern that you start to recognize that as radical 2 over 2. It's just nice to know. You don't have to, but it is nice to have in your back pocket. Cool. Done. Number 2, done. All right. Number 3, sine of 2 pi over 3. Okay. So there's our angle. No units, so we know we're in radians. And they want sine at that spot. So is that x or is that y?
Y.
Good, right? Because cosine is x and sine is y. Cosine comes before sine in the alphabet, x comes before y. And so just go to 2 pi over 3, open up that angle to 2 pi over 3 on the unit circle, and just pick the y value of that coordinate. What do you get?
Square root of 3 over 2.
Perfect. Radical 3 over 2. Okay, and that's another one of those irrational ones. It's the only other irrational number on the unit circle. And it's just nice to know that that decimal approximation is about 0.866. Okay, you don't have to. It's just helpful. If you are jumping in the calculator and you get an answer like that, you know what you're looking for. Done. 3 over 2. Cool. All right, one more sine or cosine one. I got cosine. I think it's 4 pi over 3. Was that the one that I went for? I should probably just move my laptop. 4 pi over 3. Yeah. Okay. So it's cosine, so we're going to x. Okay, go to 4 pi over 3. What's the x value at that spot?
Negative 1/2.
Perfect. Negative 1/2. Done. Okay, that's what all those are going to look like. Sine and cosine doesn't get any easier. As long as you know that cosine is x and sine is y, this gets super easy. Okay, done. Okay, 1 through 4, all good. And I could ask you for any unit circle spot in here. I just picked 4 different ones, 1 with a degree and 3 with radians, because that's probably about the ratio of degrees to radians. We're going to see way more radians than we'll ever see degrees, but we will see both. Okay, and you can see with number 5, degrees come back, and that's okay. But now that we start dealing with things that aren't sine or cosine, things could get a little bit more complicated. We just have to deal with more. We have to deal with either, in this case, like y over x, like 2 different parts. Like I need both parts of the coordinate to do it, or I have to deal with reciprocals where I start flipping fractions. Okay, with tangent. Okay, again, I'm going back. I can see it. I don't know if you can, but my basic trig ratio setup that we have is that tangent of theta is defined to be the y value over the x value. And so I know I've got some fraction here. Okay, and it could be really ugly, right, if I end up with a fraction on top or a fraction on bottom. But because I'm at 180 degrees or 90 degrees or 0 or 270 or 360 or any of those quadrantal angle spots, right, where you end up on an axis, we've just got ratios with 0s and 1s, which could be okay. So 180 degrees. Go to 180. Okay, so you're at kind of the opposite side of where we started. Okay, the y value at that spot is 0. Right, and so I just put that number on top of the fraction because tangent is y over x. On the bottom goes the x value, which is -1. What's 0 divided by anything that's not 0?
Zero.
And if you've got a calculator handy, type in tangent of 180 degrees, make sure you're in degrees, press enter, it's going to spit out 0 for you. Okay, so you've always got the calculator to kind of start backing you up a little bit so you know what's going on. Cool. All right, so that warms you up a little bit into some of the more complicated stuff. All right, let's really dive in. Tangent of pi over 2. I know it's a fraction right away, okay? If it's going to be tangent or cotangent, I know I have both y and x in there, so I'm going to create a spot where, because it's tangent, the y value goes on top, the x value goes on bottom. All right, so open up that angle to pi over 2. So we're at the top of the unit circle there, right? The y value way up at the top there is 1. So that number goes on top. The bottom is going to go x. The x value at pi over 2 radians is 0. Okay. What's 1 divided by 0?
Zero.
No.
1.
0 on top is okay. 0 on bottom, we know is not good, right? When we had 1 over 0, when we were dealing with like rational functions, there was a vertical asymptote at that spot, right? That doesn't give us an answer. So what's the best way to write a fraction like this? What's the best way to kind of say that we're not able to get a value back for that kind of fraction?
Undefined.
Perfect. Okay. And what we start to see is that some trig ratios have spots along the way with the unit circle where we're not going to get an answer back. Okay. The nice part about sine and cosine, because it's just the x or the y value, we know we're going to get a number. The domain of cosine and sine, all real numbers, right? Negative infinity to infinity. Plug in any number you want, you're all good. But every other trig ratio, tangent, and all the reciprocals are going to have some spots where we could be dividing by 0, okay? And when we graph these, you'll see we're going to draw asymptotes at those spots, okay? Cosine and sine go on forever, which is nice, okay? So number 6, undefined, okay? Undefined for sure. All right, cool. All right, now let's start getting into some reciprocals. Secant of pi over 4, okay? This is where things start to take a turn, and you really need to start understanding relationships between these trig ratios. And what I think of best, and this is what I started with when I started talking today, is that if I can relate it back to one of the 3 basic ones, I'll just flip it, okay? Secant doesn't have a co in its name, which means its reciprocal does. And so I know I'm looking at cosine. And all I really need to do is think about cosine of pi over 4, and then flip it, take its reciprocal, okay? So when I see secant of pi over 4, I immediately think cosine of pi over 4. So that's what I'm going to do. I'm going to go to pi over 4. I'm going to go to 45 degrees. Anything that has a 4 in the denominator is a multiple of 45. Okay, so cosine of pi over 4 is the x value, right? The x value at pi over 4. And that's radical 2 over 2. But that's cosine. My job is to now flip that and put the 2 on top and the radical 2 on bottom. Okay, that's the secant of pi over 4. Okay, of course, we'll rationalize that denominator by multiplying top and bottom by that square root. So we get 2 root 2 over 2, right? Because when I multiply numbers that don't have a square root with numbers that do, I can't really put them together, so I just put them side by side. But these, square root of 4, so cool, that's 2. The 2's will actually cancel that are both on the outside. Numbers outside the square root go with numbers outside the square root, numbers inside with numbers inside. And so the best version of that final answer is actually the square root of 2. Okay, the secant of pi over 4, just the reciprocal of cosine of pi over 4. And we get a nice square root of 2. Okay, stop me if you have questions. I really want to get to the point where you have time to practice. So I'm going to keep rolling along here. Number 8, cosecant of 150 degrees. Okay, degrees are back, good. They're going to happen sometimes. But before I even think about going to 150, I want to know which value I'm looking for. And so I look at cosecant, and I know that that's one of my my reciprocal ones because it's not sine, cosine, or tangent, the one I'm familiar with. And so I have to think about which one I want to go back to. Well, cosecant already has a co in the name, which means its reciprocal doesn't. And so I know I'm looking for, well, it can't be cosine, so it's got to be sine, right? Because tangent and cotangent, those are the easy ones to remember. So I'm really thinking about sine of 150 when I see cosecant of 150 degrees. So I go to 150, open up that angle into the second quadrant, 150 degrees, and I just look for the y value. But what I want to do with that y value is flip, okay? So I know I'm going to have myself a fraction, okay? Well, cosecant, so sine of 150 degrees is the y value at that spot. The y value at that spot is 1/2. Flip that upside down, you get 2/1, which is just 2. Right? And so some reciprocal values, not so nice, right? I had to flip it upside down, and then I had to rationalize, and then I had to simplify. I get something, a whole lot nicer than what I started with. Some of them are really nice, right? Flip 1/2 upside down, flip 1 or -1 upside down, really, really nice values, okay? Some of them, of course, not so nice. All right, just a couple more with me. Let's get to cotangent. We haven't done that one yet. Cotangent of 3 pi over 2. Okay, so it's cotangent. So really, you can think about it as being a tangent upside down. Cotangent's really nice, though, in that it's already written as the fraction x over y. So I don't care if you think about taking y over x and just flipping it, or taking x over y, which is just the same thing anyway. And so that's what I'm going to do. I'm going to go to 3 pi over 2, so all the way down to the bottom of the unit circle, 270 degrees. And the x value is going to go on top, and the y value is going to go on bottom. Okay, so let's see. If you're at 270 degrees, 3 pi over 2, the x value at that spot is 0. And the y value at that spot is -1. Zero's on bottom, no good, right? Zero's on top, that's okay. That's just 0. Okay, now your graphing calculator does not have these 3 buttons. Okay, you would actually have to type in like 1 over cosine, 1 over sine, 1 over tangent of whatever your angle was to be able to get these kind of answers. So if you went into your calculator, you typed in 1 over sine of 150 degrees, it'll give you 2, right? 1 over tangent of 3 pi over 2 radians, it'll give you 0. Okay, so you just got to watch out for that. All right, a couple more. Cosecant of 0 degrees. So we just haven't opened up an angle yet. So I'm here. I'm just at the very, very beginning. And when I think about cosecant, okay, it already has a co in the name, so its reciprocal doesn't. So I'm really just thinking about sine. And what I want is the sine of 0 degrees, and then I'll take that fraction and I will flip it upside down. Okay. Well, if I haven't opened up an angle yet, that means I haven't gone up from the x-axis yet, which means I've got a fraction, right? Because I'm about to flip something, but the number that I'm flipping is 0. Now, it doesn't matter what version of 0 you want. 0 over 1, 0 over 2, 0 over 5, 0 over -10, 0 over anything, as long as it's not 0. Usually the one that will flip upside down is something like 0 over 1. So let's call this 1 over 0, just like number 6. Anything divided by 0 is undefined. Okay, there you go. Okay, 2 more. This is where stuff gets fun. All right, cotangent, I like these, of some angle 5 pi over 4 that is not quadrantal. Okay, this is actually in a quadrant somewhere. And so what we need to start thinking about is that when we deal with tangent or cotangent, and we're inside a quadrant somewhere, you've got y over x or x over y in this case. And if you're inside a quadrant, it's either like 1/2 radical 2 over 2 or radical 3 over 2. And you've got fractions on top and fractions on bottom, right? So I've got this fraction, right? X is going to go on top and y is going to go on the bottom, okay? And this could work out really nicely or it could be a little rough, okay? I picked a really nice one to start, because if you think about cotangent, that being x over y, and you go to 5 pi over 4, okay, a multiple of 45 is one of these. Multiples of 45, they have the same x and y value, just maybe positive and negative we have to watch out for, right? And so the x value of the spot, negative radical 2 over 2. All right, that's x at 5 pi over 4. But so is y. And you've got some number divided by itself, which is the same as like 1 over 1, 5 over 5, 3 over 3, pi over pi, negative 7 over negative 7. Anything divided by itself, as long as it's not 0, is 1. So nice that it works out that way, right? But it doesn't necessarily have to. Right? We might end up with something else, okay? And that's what number 12 starts to get at, okay? The tangent of pi over 6. And what I wanted to do with this last one is show you as ugly as it can get, okay? Everything else is as ugly or just a little bit easier, okay? Tangent or cotangent is the only pair of trig ratios that have both y and x in them. And again, pi over 6 is inside the first quadrant. And so I know I've got a fraction over a fraction here, which is why my middle fraction bar is so much bigger, okay? You can see the width of my fractions were relatively small as I was working through these, but tangent and cotangent, look how big I made that fraction bar so that you can clearly see the division between the top and the bottom, okay? When they were the same number, exactly perfect, 1. If this was like cotangent of 3 pi over 4 and one of them was positive and one of them was negative, sure, okay, I'll just put a negative in front. But when you get to things that aren't multiples of pi over 4, like pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4, and you get to like pi's over 6s or 7 pi's over 3s or whatever, you have different numbers top and bottom, right? Tangent pi over 6 is y at that spot over x at that spot. Okay, so when you open up an angle at pi over 6, the y value there is 1/2. The x value, which is going to go on the bottom, is the square root of 3 over 2. Okay, and you've got a fraction over a fraction. You've got a complex fraction that needs to be simplified. Okay, and there's a couple of different ways to do it. Here's the long way over here that I just want to kind of separate for you so you can see. But I hope that you do it the easier way here in a second once we do, okay? A fraction, like 1/2, divided by another fraction can be rewritten as the first fraction times the reciprocal of the second one, okay? Copy, dot, flop, keep, keep, change, flip, whatever you learned in middle school with dividing fractions, or even in Algebra 2 last year when you did simplifying rational expressions. Keep the first fraction the same, change division to multiplication, and then flip the second fraction, and look what happens, right? You've got a 2 on bottom and a 2 on top, which we can, of course, divide away, okay? And those fractions get a whole lot simpler a lot faster. But why did that happen? Like, why were we able to get to the point where we had a 2 on the bottom of one fraction, but a 2 on the top of the second one? It comes back to here, which I might have said in class before, but if you are dividing fractions and their denominators are already the same, this is the situation that's going to happen if we take this step. And I know that I'm going to keep, change, flip. If I want to divide fractions, I need to really just multiply by the reciprocal of the second one, which means right from here, if you are sitting there and you notice that within a complex fraction, the denominator on top and the denominator on bottom are the same number, you can divide them away from the beginning. Keeping the fraction where it was, the one that was on top stays on top, and the radical 3 that was on the bottom of the big fraction can stay on bottom and get you to that exact same spot, okay? So keep, go for this. If you want to do it, sure. If you want to take the second to write this step, but if you notice, and that's going to happen, I mean, we're in the unit circle. Every fraction in the unit circle has a 2 on the bottom. So you know that if you're dealing with tangent or cotangent at one of those spots, you'll be able to divide away those denominators right away, which is super nice, okay? We get to here, of course, we'll rationalize, right? Multiply top and bottom by the square root of 3 over the square root of 3. So we end up with the square root of 3 over 3, and we're done. Okay, and that pretty much covers all of the types of issues that you might run into. Simple things like sine of an angle, cosine of an angle, okay, just x if it's cosine, y if it's sine. Tangent being y over x, and then all the reciprocals that go with them, potentially running into spots where 4 out of your 6 trig ratios could have a 0 in the denominator because we're dividing by x, we're dividing by y. In one of those cases. Okay. Of course, those can only happen at quadrantal spots because that's the only time we'll ever get a 0, right? 0 is going to happen for y at 0 and 180. 0 is going to happen for x at 90 and down at 270. Okay, cool. So there you go. I wanted to make sure that I walked you through those, but I also want to give you a chance to try some others on your own. And so what I want to make sure we do, sorry if the screen's so blurry. I will definitely take a picture of this work and I will post that on today's announcement so that you can look at it. You know what, I will actually do that right now. I want to first, though, give you a chance to get started on practice for yourself. If you go back to today's practice where you found these 12 problems, I hit some practice for you right there. Okay, so part 2, 13 through 23. I mean, we only have like 10 minutes or so. So you might not be able to work through 11 problems in 10 minutes, but maybe you can. What I do have over here, when you're ready to peek, so peek when you're ready, I have the answers. Okay, I did these during second, and so I have the answers right there. Let me make sure that the angle is okay. So what I'm going to do, I'm going to take pictures of both of these, and I will post them on Canvas right now. Okay, let me do that. Okay, it's going to take me a minute because I have to upload it to Drive. But there are the solutions to 13 through 23. Again, nothing you need to submit for me. It was really, I just wanted to give you a chance to try these out. So stick around and get these done if you can. And then we will go from there tomorrow. We will meet back tomorrow. Nothing you need to do ahead of tomorrow. We'll probably live stream tomorrow and Thursday. And then we will stop right there. I'll have some practice for you maybe for Friday. We'll see how far we get. I'm really not sure how far into this we'll get. We didn't get quite as far today as I was hoping, and that's okay. I'd rather prepare for more than less. But I wanted to ask you about next week. Obviously, we've taken our final, right? So we're done. There is nothing beyond maybe a practice for Friday that I'll have you do. We'll do like 4.2 or 4.3 kind of practice or something like that. But next week, during finals week, I don't know what to do that's best for you. We have an hour and a half blocked off for the final. I'd like to actually hear from you. So you tell me what you think. Would you rather take that time to focus on studying for other finals? Or would you, so that's option number 1. Absolutely nothing from me besides just checking in like a little attendance form so I know that you checked Canvas and that you're here. Option number 1. Option number 2 would be to have class. Like I would just keep teaching. We'd have like one last trig day. Or kind of an in-between option, option number 3, where I send out like an optional practice. Like, come if you want or not, but if you do show up and you do some work and you submit it, I'll give you some credit for it. So option number 1, don't do anything. Option number 2, have class as if it were, as if we had an hour and a half to just have class. And option number 3, an optional extra credits, kind of not a whole lot of extra credit, but a little something to show up for the hour and a half, work through some stuff, and submit it. What do you guys think? Drop your choice in the chat if you have a preference. Number 1, nothing next week. Number 2, have class for an hour and a half, like a mandatory class for an hour and a half, where we keep going with trig, because man, it would be so nice to get an hour and a half of trig in that we wouldn't need to then take 2 days to do when we get back. Or option number 3, an optional class where if you show up and you do the work, I'll give you a little extra credit. Okay, lots of 1s and 3s. No big surprise that the mandatory class during finals week option didn't go over all that well. Okay, cool. All right, so I will let you know what I decide. I got basically the same response from period 2 as well. So, okay, let me upload these photos to Canvas. Give me a sec. So what I'm going to do is I'm going to go right to today's announcement. I am going to, right underneath where it says click here for today's practice, I'm going to put notes number 1 and notes number 2, and I will link them to these photos. Let me open up my drive and get there. So go ahead and try those 11 problems. Check your answers as you go. You'll want to at least have them done and ready for tomorrow, so you feel good about where you are, so we can keep going. I can't keep going unless I know you're ready, okay? You know what, I'm going to call them answers to part 1 from practice and answers to part 2. How about that? Okay. All right, so I saved it so that you can look at least part 1. I'm going to do part 2 right now. So if you refresh your announcement, you will be able to see much more clearly, hopefully, the work that we did for part 1. And I'm going to do part 2 right now. Answers to part 2. And saved. Okay, so those are good to go. So if you need to take a look to be able to see that more clearly, please do so. Thank you for letting me know which option you preferred. I was leaning towards 1 or 3 for sure. The extra credit that you would get an opportunity to do wouldn't be much, but it would be something. But it wouldn't be anything new because it's optional. So it would be one of those things where we kind of take whatever we learn up through Thursday, and we just take some time to practice it, work on it, so that if you didn't come, you wouldn't be missing out on anything you would need to know for when we get back in January. Okay. It's 11:15 now, so if you have places you need to be, feel free to head out. If you have questions about these are all really nice problems that could come up, right? And you see that they're mostly in radians, right? Only the first 2 were in degrees here for part 2, because that's what's going to happen. We're going to be mostly in radians, and radians are better. So hopefully this all makes sense, and you can look through this and get a good sense for how to get these done. Definitely want to have these ready for tomorrow, at least that you can understand how to do them. Again, nothing to submit. Other than that, on today's announcement, I also put a link to, at the very, very bottom, just a feedback form in case there's something about class that you like, you don't like. Now that we're fully remote, I really want to make sure that I'm doing the best for you guys. So it's optional, and if you want, it can be anonymous. The first question is, what's your name? But it's super optional to put that in there. I didn't make that required. But if there's something that you thought would benefit me as a teacher, I always want to get better as a teacher. And of course, that benefits you as a student or as a group of students. I'm all ears. I want to know what's working for you with this class or even with other classes that maybe I could try. As we head into January, it looks like we'll probably be remote still, at least to start. So I just want to get better. I just want to be better for you guys. So if you're good, you are free to head out. If you want to stick around and finish up these questions, or work through that at your own pace today, so that they're ready to go for tomorrow, that works for me. Thank you all for being here, and I will see you again tomorrow. See if I can stick my head in a place that's not.
Thank you.
Thank you.
Bye, Rosie. Thank you.
Bye.
Thank you.
Bye. Thanks, guys.
See ya.